Good morning. Uh, in the today's video lecture, we further make the discussion regarding the dual nature of the radiation. Last class, we have considered the photoelectric effect, which actually exhibit the particle nature of the radiation. The radiation, the electromagnetic radiation specifically of suitable frequency or wavelength incident on the metal surface going to emit the electrons from the surface. To explain the whole experimental result, one cannot uh, use the classical idea. There is a wave nature of the radiation, and naturally one has to consider the particle nature of the radiation, where the radiation imagined to be or supposed to be the stream of energy packets or the bundles. Each one is now having the energy equal to h nu, where the h is a Planck's constant, nu is frequency of radiation, by which one can explain the whole phenomenon of the photoelectric effect. Now further, the quantum nature of the radiation, the particle nature of the radiation exhibited in case of a striking phenomenon which is referred as the Compton effect. And let us discuss regarding the Compton effect. And the Compton effect was discovered by American physicist Arthur Compton in 1923. And Compton actually did the experiment regarding the scattering of the X-rays. X-rays are in the experiment, he used the X-ray beam, and then it is now made to incident on the scattering material substance such as the graphite block, and he found that the scattered X-rays and the wavelength of the incident X-ray is, let us say, lambda 1, and the scattered wavelength is lambda 2, and Compton observed that lambda 2 is greater than lambda 1. Therefore, the X-rays are made to incident on the scattering substance such as the graphite block or the metal surface, and the scattered X-rays are received by the detector, by which he measured the wavelength of the scattered X-rays and found that there will be increase of the wavelength of the scattered X-rays. Lambda 2 is greater than lambda 1. And actually it is due to the incoherent scattering, where the energy of the scattered radiation is not same as the energy of the incident X-rays. And therefore in the phenomenon where the electromagnetic radiation of the very high frequency such as X-rays or the gamma rays now incident on the scattering substance, during the scattering there is an increase of the wavelength of the scattered radiation, and that phenomenon was referred as the Compton effect. Now how to explain this whole phenomenon of the Compton effect? For that Compton used the quantum theory, and in between the 1900 where Max Planck proposed his quantum theory, and the 1923 almost the 2 decades passed, and the quantum theory was made to apply in the different phenomena such as the photoelectric effect and the specific heat of the solid, and similarly the principle of the laser and so on. Therefore it is not surprise that Compton used the quantum theory to explain this whole phenomenon, where there is an increase of the wavelength of the scattered radiation during the scattering process. Now we consider the theory of the Compton effect. Now let us consider the theory of the Compton effect. Theory of theory of Compton effect. Now, let us say this is the incident X-ray beam, and it is incident on the so this is the original direction. Phi is now become what we have the scattering angle. It is assumed lambda 1 is now the incident wavelength, lambda 2 is now the scattered wavelength, and therefore lambda 1 is greater than lambda 2. Or this is a small change in the wavelength due to the scattering that we can write as a delta lambda. Now, to explain the whole phenomenon, Compton used the quantum theory, where he imagined the collision between a incident photon, let us say this is a electron, and this substance contains a large number of the electron. As you recall, in the case of the photoelectric effect, to explain the phenomenon of the photoelectric effect, Einstein used the idea that the photon now make the collision between the electron. In the same fashion, Compton used the idea that the electron and the incident X-ray beam, which is a stream of the large number of the photons, therefore a photon of the particular energy h nu is now make the collision with the electron, and here for simplicity case let us assume that the electron is at rest. Therefore this electron, it is at rest, and the collision between a photon of energy, I'll write this energy as E1, and therefore E1 equal to h nu. Or in terms of the momentum, we can write this one as the momentum as P1 equal to h nu by c, or I can write this one as P1 into c is equal to h nu. And how you got this one, the momentum? Because according to you are going to study about the de Broglie hypothesis. According to the de Broglie hypothesis, I will write here P is equal to the momentum of the particle, P is equal to h by lambda, and therefore, and also we know that it is a wave packet nu lambda equal to c, or lambda equal to c by nu. Therefore, if you substitute here, it is become h by the lambda equal to c by nu. Therefore, this is become h nu by c, that we have written here. Therefore, the incident photon of the energy h nu, or the momentum h nu by c, make the collision with the free electron on the this substance. This electron is now at rest, but it is now having the energy. That energy let us write as the inherent energy of the electron, which we know that according to the Einstein's idea, it should be equal to m naught into c square. Now, what is the momentum of this electron which is at rest? And that momentum naturally equal to 0. And the scattering is now takes place. Therefore, at this direction, let us say we have the X-ray is now gets scattered. Therefore, the X-ray photon is now travel along this direction, and this can also be written as hc by lambda 1. What is lambda 1? Lambda 1 is now the wavelength of the incident of X-ray and the photon. And let us consider lambda 2 is now the wavelength of the scattered photon. And what is the energy? The energy we can write as E2, and this E2 can be written as the h, okay, write this as nu1, h nu 2, and the momentum of this photon, scattered photon, I can write as the h nu 2, okay, this is nu 1, h nu 2 by c, or this P2 into c is equal to energy h nu 2, and therefore this is become the scattered photon, and this is the original direction. Suppose if the scattering does not take place, the X-ray photon should travel along this direction. Now naturally, what is this angle? This angle is now become what we have the scattering angle. Now it is a collision between a photon and the electron, and that is why this electron now recoils, moves in the other direction. Let us say it moves along this direction, and therefore this is now become what you have the recoiled electron, and whose energy E is equal to mc square, and it is a moving with the velocity v, let us say. Therefore what is the momentum of the electron? That is equal to m into v, where m is now the mass of the electron. Therefore phi is now become what we have the scattering angle. Therefore the whole phenomenon can be explained simply by uh, considering uh, the collision between the X-ray photon and the electron which is at rest, and the electron takes the energy and it travels along this direction, and the photon now travel along this direction. Therefore this is phi is now become scattering angle. Now in the whole process, the electron takes now some amount of the energy from the photon. That is why the scattered photon is now having a lesser energy. Suppose if the energy is now lesser, what happens to the frequency? The frequency decreases and the wavelength naturally increases. Consequently, the wavelength is now going to increase, which is nothing but what we call as the Compton effect. Therefore, the Compton effect is just a phenomenon where the X-ray or the gamma rays of the very high frequency, when incident on the scattering substance, the wavelength of the X-ray is now going to increase, radiation going to increase. Now, once we know this, just we can apply the law of conservation of energy. Therefore, the first we consider the applying law of conservation of energy. Let us apply the law of conservation of energy. Now, what is the law of conservation of energy? Says the total energy before the collision should be equal to the total energy after the scattering, after the collision. Therefore, the initial energy, that is E1. What is the energy of this one? The m naught c square equal to E2 plus energy of the, the recoiled electron E, or this is equal to E1. E1 equal to, I can write this one as h nu 1 plus m naught c square E2 equal to h nu 2 plus E equal to mc square, or we can write this one as this h nu 1 plus m naught c square equal to h nu 2 plus mc square, or I'll write this one as, what is h nu 1? H nu 1 can be written as P1 into C. Therefore, this is become P1 into C plus m naught c square equal, what is h nu 2? H nu 2 equal to, in terms of momentum we have written P2 into C plus mc square. Okay, then let us write this as equation 1. Or this C, can write this one as P1 minus P2. C into, I have taken this side, C into P1 minus P2 plus m naught c square equal to mc square. And let us write this as equation 2. Therefore, we apply the law of conservation of energy. H nu 1 plus m naught c square, inherent energy. Energy, this electron is at rest, but it is now having the energy m naught into c square. What is m naught? The rest mass of the electron. M naught c square equal to h nu 2 plus mc square, and it is moving, therefore its mass changes, therefore m into c square, electron moving, mass changes, and let us say m is now the mass of the moving electron, therefore it is mc square, and the h nu 1 can be replaced by P1 into C, and that we are already here. Therefore P1 into C plus m naught c square equal to P2 into C plus mc square. We rearrange the equation. Now let us square this. I will square this. Yes, you try this. What you will get on squaring, this is become c square, and p1 minus p2 if you square, p1 square, p2 square, a minus b whole square, minus 2p1 p2 minus 2p1 p2. This term we have squared, a square plus b square. Here it is now m naught square c to the power 4. What is the next term? 2 m naught c square, c square into c. Therefore it becomes c cube. Please check, I make a mistake also. p1 minus p2. You are squaring this one. Therefore this is become m square c to the power 4. I will write this as equation 3. Therefore, slight mathematical jugglery we make, and therefore m square c to the power 4, and you get this one. Now you see this electron is now recoils with a particular velocity, and it is a very high velocity. Therefore, its mass varies with the speed, and we know that according to the Einstein's mass energy relation, already we have studied that. And what is the Einstein's mass energy relation says, and it is m equal to m naught by square root of 1 minus v square by c square. Now let us square this, and I will square this and slightly make the rearrangement. Therefore m square and m square equal to m naught square, and this is, you have to square this. Therefore this will become c square minus v square, and denominator c square, that goes to the numerator. Therefore I can write this one as m square equal to m naught square c square divided by c square minus v square. And let us cross multiply this. M square c square, I will take this m square minus v square to the right hand side. Therefore simply m square v square plus m naught square c square. Is it right? But here we have the m square c to the power 4. What we can do to get this, we multiply by c square. And if we do that, m square c to the power 4 equal to m square v square c square plus m naught square c to the power 4. Now what is m square c to the power 4? M square c to the power 4 equal to m square v square. That is now the momentum of the electron, which I will write as the PE, the momentum of the electron. Therefore this is become PE square c square plus m naught square c to the power 4 equal to m square c to the power 4. Let us write this equation as equation 4. Now we have the m square c to the power 4 from equation 3, m square c to the power 4 expression from the equation 4. Now you can equate these two, and therefore I will write here, straight away I will write here, what is m square c to the power 4, and for that you will bring here. Therefore this is become p square c square plus m naught square c to the power 4, and this term. Okay, that is now become the, let us say, this equation. Now here c square term, m naught square c to the power 4 cancel, and therefore simply we have right here p square c square, this one equal to c square, what is the bracket, p1 square plus p2 square minus 2p1 p2 plus 2 m naught c cube p1 minus p2, and I will go here, and therefore this c square we cancel. Therefore ultimately we get the expression for the momentum. P square is equal to, c square cancels, what is p square, p1 square plus p2 square minus 2 P1 P2 plus 2 m naught. This is c square, here c cube. Therefore, what is the remaining? That is c into P1 minus P2. Okay, let us write this as equation 5. I'll repeat again. Now, collision takes place between a photon and the electron. The electron is now assumed to be at rest. Apply the law of conservation of energy. H nu 1 plus m naught c square before the collision. After the collision, H nu 2 plus mc square. H nu 1 is equal to P1 into C. Therefore, m naught c square P2 into C plus mc square. Rearrange the equation, squaring, you get this one. Then, to using the Einstein's mass energy relation, you have m equal to m naught by square root of 1 minus v square by c square. And so that squaring and rearrange the equation, you will get m square c to the power 4. Substitute here, and then c square is now taken out, deleted by dividing by c square, and you get the Pe square equal to P1 square plus P2 square minus 2P1 P2 plus 2m naught c into P1 minus P2. Now, if you could consider here, what is Pe? The momentum of the recoiled electron. P1, P2 are the momentum of the incident photon and scattered photon respectively. And m naught is the rest mass of the electron. P1 minus P2, that is now actually the difference of the momentum of the incident photon and the scattered photon. Now we consider the law of conservation of the momentum. Therefore, applying law of conservation of momentum. Let us apply the law of conservation of momentum. Now, the law of conservation of momentum, if you apply, the momentum is a vector quantity. Therefore, the initial momentum, I'll write as P1. What is the momentum of the electron which is at rest? Therefore, it is 0. What is the momentum of the scattered photon? That we have written as P2. What is the momentum of the recoiled electron? That we have written as P. Or we can write this one as Pe equal to momentum of the electron is equal to mistake here. P equal to P1 minus P2. Now let us square this. If you square the two vector product squaring, that means it is become simply P square. This is become P1 square plus P2 square minus 2 into vector P1 into vector. This is a dot product of the two vectors. It is a dot product of the two vectors. Vector A dot vector B is equal to AB into cos pi. What is the cross product? Vector A cross vector B is equal to AB into sin pi or the sin theta, where the theta is the angle between the two vectors. In this case, it is now this vector is the P1, this vector is the P2, and therefore the phi is the angle between the two vectors. Therefore, this is become P square equal to P1 square plus P2 square minus, what is this one? 2P1 P2 into cos phi. Therefore, I'll write this as equation 6. Now we got this P square. We can substitute in the equation 5. Therefore, if you substitute in the equation 5, it is become P1 square plus P2 square minus 2P1 P2 cos phi is equal to P1 square plus P2 square minus 2P1 P2 plus 2m naught c into P1 minus P2. And this term P1 square cancel here. Similarly, P2 square cancel, and therefore we have the minus 2 P1 P2 here, minus 2 same, therefore we take out the 2, divide by 2, and then I will take this P1 P2 to this side, and that means simply it is become P1 into P2. What is this one? 1 minus cos phi is equal to 2 cancelled, and therefore this is now m naught c into P1 minus P2. Or I will write here this similar term, let us write one side, and therefore I can write this one as okay, I will take this m naught c to this side, and therefore this is this equation we can write as 1 minus cos pi is equal to P1 minus P2 divided by P1 P2, or how we can write this one as 1 by P2 minus 1 by P1. You get this one. Is it right? Okay. Here we have taken m naught c to this side. Therefore, this is become m naught c. Or in other words, this, what is P? P is equal to h by lambda. Therefore, 1 by P2, 1 by h by lambda 2, that goes to the numerator. Therefore, simply it is become lambda 2 by h minus lambda 1 by h is equal to 1 minus cos pi divided by m naught into c. Or this leads us to lambda 2 minus lambda 1 equal to h by m naught c into 1 minus cos pi, or change in the wavelength h by m naught c into 1 minus cos pi. This is the beautiful expression for the increase in the wavelength due to the Compton scattering. Therefore, the change in the wavelength due to the scattering is now lambda 2 minus lambda 1, and lambda 2 is the wavelength of the scattered beam, and lambda 1 is the wavelength of the incident beam, and lambda 2 minus lambda 1 is now small change in the wavelength, which is given by delta lambda equal to h by m naught c into 1 minus cos pi. This equation gives us the whole idea regarding how during the collision between the photon and the electron, which changes the wavelength of the incident radiation. This derivation is extremely important, not only in the point of view of physics, but in the point of view of examination. Usually, for the full 7 marks, this derivation is asked in examination. Derive the expression for the change in the wavelength due to the Compton scattering. Therefore, we applied the law of conservation of energy. Then we have made a slight mathematical jugglery to get this P square C square. Then using the law of conservation of momentum, and you got P square, and similarly here the P square, and then we substituted for that this equation is now become the P1 square P2 square minus 2 P1 P2 cos pi is equal to P1 square plus P2 square minus 2 P1 P2 plus 2 m naught c into P1 minus P2, and therefore we have ultimately we have got the expression as the delta lambda equal to h by m naught c into 1 minus cos pi. Please go through the full derivation. Just a very simple mechanics is now used to explain the whole phenomenon, that is the X-ray beam which is now the invisible. The scattered beam is now invisible. The electron is now invisible. And that invisible but observed phenomenon, to explain that, a very simple the mechanics is used. In fact, this particular research paper was written by Compton. It comes in the history of physics, and it was sent to Albert Einstein to get the review. And Albert Einstein went through this whole paper, and then he sent a telegram or the comment, and he said that one of the beautiful explanation I have come across in the recent times, which going to explain the whole phenomenon of the incoherent scattering. Okay, now we got this expression, change in the wavelength due to the scattering is equal to delta lambda equal to h by m naught c into 1 minus cos phi. Now let us go slightly further. Now if you consider this expression, h is now a Planck's constant, it is a constant. M naught is the mass of the electron, it is a constant. C is now anyway, the velocity of the light, it is a constant. Therefore, we have this constant term. We can evaluate what is the value of this h by m naught c. H is equal to 6.63 into 10 to the power minus 34 joules second. That is the value of the Planck's constant. And what is the mass of the electron? That we already know, 9.1 into 10 to the power minus 31 kg. Velocity of the light, 3 into 10 to the power 8. And this comes out to be something, if you find out, 0.48 into 10 to the power minus 10 meter, or it is equal to, I can say this is now 0.48. Sorry, I made a mistake. I think it is 0.024. Just I'll check that. Okay, 0.24. I made a mistake. 0.024 into 10 to the power minus 10 meter, and it is 0.024 angstrom. Therefore, delta lambda equal to 0.024 angstrom. Now, this particular one is a constant. This is also known as what you have the Compton wavelength. This is the Compton wavelength, 0.024 angstrom. Now, if you use this one in this equation, let us say this equation, some equation 6 or 7, then delta lambda equal to 0.024 into 1 minus cos phi. Now, if you observe here, the change in the wavelength is now entirely depend upon the scattering angle, the phi. It does not depend upon the scattering substance. It does not depending upon the nature of the substance. It entirely depends upon the scattering angle. Now, what are the values of the cos phi you can think of? Suppose, let us consider the different cases, and the phi equal to 0 degree. That means there is not at all any scattering. Simply the way the X-ray beam is now incident on the scattering substance. Suppose if this is a scattering substance, X-ray beam is now incident on the scattering substance, and like this, and it does not travel in the same direction. There is no angle of scattering, and in that case, what is delta lambda? Delta lambda equal to 0.024 into 1 minus cos phi. Cos 0, that is equal to 1. Therefore, 1 minus 1, that is equal to 0. Delta lambda equal to 0. That means lambda 1 equal to lambda 2. There is no change in the wavelength. And let us assume that the second case, when phi equal to 90 degree, what is the value? Value is now comes out to be delta lambda equal to 0.024 into 1 minus cos 90 degree. What is cos 90? Cos 90 is equal to 0, and that means delta lambda equal to 0.024 angstrom. That means the lambda 1 minus lambda 2 equal to 0.024 angstrom. And if you know the lambda 1, and you can easily find out what is the value of the lambda 2. Lambda 2, sorry, I made a mistake. Lambda 2 minus lambda 1, lambda 2 minus lambda 1 here. Lambda 2 minus lambda 1, and the lambda 1 we know lambda 2 is equal to 0.024 plus lambda 1. And let us assume third case where the maximum angle of scattering, naturally it is 180 degree. Therefore, if you take the phi value is equal to 180 degree, then what is the value of delta lambda? Delta lambda is equal to, you can say easily, 0.024 into, what is the value? 1 minus cos 180 degree. What is the value of cos 180 degree? That already you know, minus 1. Therefore, 1 minus of minus 1, that is become plus 1, and it is 0.024 into 2. 0.048 angstrom. Therefore, the minimum change in the wavelength, naturally, there is no change in the wavelength, it is 0. The maximum change in the wavelength is now 0.048 angstrom. That means, if the incident wavelength is now having a 1 angstrom, let us assume the X-ray beam of the wavelength 1 angstrom incident on the graphite block. Now, what is the maximum change in the wavelength? That is now lambda 2, and it is 1 plus 0.048. It is now become 1.048 angstrom. 1.048 angstrom. Therefore, very small change in the wavelength now happens during the scattering. Just the beam is now incident, gets scattered, and the change in the wavelength is now happens is now only of the order of 0.048 angstrom. It is not more than that, and therefore this is now extremely small value. Now this extremely small change in the wavelength actually make a criterion for observing a Compton effect. Now, whether the Compton effect is now observed in the all type of the radiation? No, there is not possible, because in case of the light, what is the wavelength? The wavelength of the light is of the order of 4000 angstrom to, we can say, 8000 angstrom, and the 400 nanometer to, we can say, 800 nanometer. That means it is from the one end it is ultraviolet, and other one it is the red or the infrared end. Now, suppose if the incident wavelength is of the order of 5000 angstrom incident on the graphite block, and the light gets scattered, and there is a change in the wavelength of the photon now happens, and there is a small increase in the wavelength, and 5000 angstrom it is now the incident wavelength, and the scattered wavelength is now become hardly 5000 plus 0.048, and one cannot observe. And if you calculate what is the fractional change of the wavelength, and it is now of the hardly about 0.005%. That means one cannot observe the phenomenon of the Compton scattering in case of the visible light, but it is now appreciable in case of the X-rays, or it may be in the case of the gamma rays, because they have become the highly energetic and they are very short wavelength. Since it is now the very short wavelength of the radiation, during the scattering, the change in the wavelength one can observe. Now we have said that the electron is now recoiled in a particular direction. Let us say the mc square. Now what will be the kinetic energy of the recoil electron? One can find out the kinetic energy. And the kinetic energy of the recoil electron, I will write here. If you consider the kinetic energy of the recoil electron as E, or I will write here, kinetic energy of recoil electron. Now we said that the collision now happens between a photon and the electron, and the electron takes energy and it now moves. And therefore the difference of the incident energy of the photon and the scattered photon will be taken by the electron, that is going to manifest as the kinetic energy of the record electron. Therefore the kinetic energy of the record electron, if you write as a EE, and that is equal to the energy of incident photon minus energy of scattered photon. What is the energy of the incident photon? That we have written as h nu 1. What is the energy of the scattered photon? That is now equal to minus h nu 2. And this this is also in terms of the rest mass, it is mc square minus m naught c square. Therefore, easily one can find out what is the kinetic energy of the record electron. If you know the incident energy of the photon, what is the energy of the scattered photon, difference of this one, which is now become kinetic energy, or simply mc square is equal to the kinetic energy plus its rest mass energy, that is become what we have the energy of the record electron. Now I'll stop here. Therefore, the whole phenomenon of the Compton effect, where the X-rays or the gamma rays of the very highest energy or the frequency or the short wavelength, when gets scattered by a scattering substance, there is an increase of the wavelength. To find this expression for the change in the wavelength, you apply the law of conservation of energy and you apply the law of conservation of the momentum, so that we arrive at the expression lambda 2 minus lambda 1 equal to h by m naught c into 1 minus cos phi, and that gives now the change in the wavelength. This change in the wavelength delta lambda is now extremely small, of the order of the 0.024 into 1 minus cos phi. What 0.024 angstrom, which we call as the Compton wavelength, 0.024 angstrom, this term. And therefore, depending upon the phi value, scattering angle, we have the change in the wavelength happens. It may be 0 degree, it may be 30 degree, 60 degree, 90 degree, 135 degree, 152 degree, any angle you can find out between the phi, the minimum 0 degree, the maximum phi, the scattering angle 180 degree, one can arrive what is the change in the wavelength. And in the next class, we solve some of the important problems in the Compton effect. This is a beautiful phenomenon, and derivation, once again, if you go through and you get the full idea, if you derive yourself this particular expression, and as an assignment, you whatever the thing which you have discussed, you have to summarize and you have to submit that summary in the as an assignment. Okay, considering the problems, let us solve in the next class. Stop here.